Okay, so in Chapter 11, we're going to continue our discussion on hypothesis testing, except in this chapter, we're going to look at comparing two populations as compared to in Chapter 10, we only basically took one sample to look at one population. So in this chapter, we're still doing hypothesis testing, except we're looking at two population comparisons. So as we start off by looking at two populations, again, this particular chapter, we still have the sigma known versus the sigma unknown scenarios. And in the first couple examples, we're going to be looking at the sigma known, and then we'll go to the sigma unknown scenarios. Now, the typical way that you set up your HO and H1 hypothesis, your null and your alternate, typically it's going to be very similar to Chapter 10. So we're going to have the two-tailed test. That's going to be one of the scenarios. We're also going to have for the alternate a greater than scenario and also a less than scenario. But the big difference is that we're going to be comparing populations when we set these up. But the basic format is still going to be the same. So as you can see right away, there's going to be a new formula to how to get your test z-value. So this is one of the differences. It's basically one of the few differences between the two chapters. And so we still have a normal curve. That's not changing. We're still going to be, and of course, since we're talking about a sigma known, this is going to be a sigma known scenario, we're still going to be looking in the z-table to get our critical values. But notice, look at the formula. You take x bar 1 minus x bar 2. So you're basically taking the sample means from the two populations. And then look at your denominator. You got your sigma squared divided by the sample size plus sigma squared 2 over the sample size 2, all under square root. Once you get your z-value, at that point, everything else is literally going to be the same for this sigma known scenario. So in this case, we're looking at the checkout time, and notice that the different customer types, you have a standard line versus a fast lane, and they're trying to figure out if the average checkout time using a standard checkout is longer than the fast lane. Okay, so they got some data that they gathered down below. Notice they've got sample means, they've got the sigma for each, and they've got the sample size for each. And so to think about how to set up your null and alternate, if you're going to label the standard, let's say as population 1, and the fast lane, let's say as population 2, then when you go to your HO, H1 scenario, you're going to be looking at the alternate. You want your population 1 to see if it's actually longer than population 2. So you're going to set your alternate up to be a greater than scenario. So therefore, the null would then have to be less than or equal to. So that's the basic idea. And then after that, you simply plug it into your new formulas. And as you can see, again, they're going to stating in here the keyword there was longer. So you want that alternate, in this case, the standard checkout lane, to see if it's faster than the fast checkout lane. And so then, of course, we've got the alpha level. That's just like before, 0.01. This is going to be, in this case, because it's greater than, this is going to be an upper tail test. And so that's still going to be alpha just like before. And so you have to go to your z-table to get your critical z-value. And then once you plug it into your new calculation, your new formula to get your z-value, then you'll make your conclusion. So again, you notice if you go down to the table, again, I'm going to be using 2.33. They're using the computer to do these numbers, so I won't expect you guys to do that. But if this area is 0.01, notice 0.49, that's going to give you this critical z-value that's right about 2.33. So then at that point, you do your test stat. You're going to compare it to that number, just like you did before in Chapter 10 to come up with your decision. And as you can see, they're plugging all these numbers in to our formula. Here's our new formula right there. Here's the actual calculation. And notice what they came up with, guys. There's your test stat result. And of course, just to kind of help you out with your decision, if this upper area is about 2.33, this number definitely falls in a rejection area. So we can reject the null and conclude that the standard lane is longer, and therefore that the fast lane is indeed faster. Okay, so and then of course, as we continue this discussion on two population comparisons, we could also have a unknown population standard deviation. So that again, that's going to be your sigma unknown. And of course, in the scenario we're going to look at next, if we have a low sample size or low number of observations, and we still have to conclude that it's still a normal curve, that even though we may not have the known standard deviation, that in fact the variability is similar and the independence idea is also still there. Since we're comparing some means and we're assuming that everything is similar in terms of the unknown standard deviations, there's basically, it's called a pooled t-test, and you got to find the value for the two different, basically it's an averaging technique when they talk about what they call a pooled t-test. So if you look at this first formula, you just kind of follow it. You've got sample size minus 1 times the variance squared plus the sample size 2 minus 1 times the variance of the second population squared, all over n1 plus n2 minus 2. That's going to give you this pooled number. It's like a weighted average. So then if you look down below, this is going to be your formula to calculate your test statistic. Notice x bar 1 minus x bar 2, so you're comparing the two populations, but it's this value right here that's going to go right there in that denominator. That's basically going to be referred to as your variability, but it's a pooled number, which is basically kind of like a weighted average number, which is going to be more true to what the population would be. So once you do that, then that, of course, is going to give you your test statistic t-value. So in this particular case, here's our two comparison. We were going to be comparing this particular population with this particular population. And of course, one of them is a sample of 5, and everything is in minutes. And so we're going to basically evaluate both methods. And of course, we're looking at the minutes as our comparison. And the key word to set up the hypothesis is the key word is difference. Difference in the average mounting times. The significance level is going to be 0.10. So once again, as you can say, it really doesn't matter in this case what you label population, which one. Again, you're just trying to see, is there a difference? So this is going to be a two-tail test. So if I set this up, remember this is still sigma unknown. We've got an upper and a lower tail, which means each of these is alpha half. So that's 0.05, and that's 0.05, again, alpha half. And then of course, we've got to get the appropriate test statistic based on our sample data. And so of course, you got to get your critical values. So again, with your degrees of freedom and your alpha level, we're going to estimate that our critical value is right about 1.833. So again, and you can kind of approximate your degrees of freedom by taking n1 plus n2 minus 2. Typically, that's a good approximation of your degrees of freedom. And then, of course, your alpha half, because it's 0.05, you'd use a critical value that's right at 1.833. And so notice, to do that pooled t-test, you've got to do all the calculations on this one. So they're showing you step by step basically how to get the variance and the sample standard deviation for the Wells method. Here's your sample standard deviation for that. Here's your sample standard deviation for the Atkins method. So once you get those numbers, you're basically going to plug these in right down here into that equation. And of course, you can see here's the calculations. You're using both of these. Here's the 2.91, there's the 2.02. You plug it in, there's your two sample sizes, and here's going to be the result of this pooled number. So this pooled number is what you're going to be using in your test statistic calculation. So as you can see, here's our formula to do the test stat, which is right there. And that's that pooled number you had to come up with. Once you plug it in, guys, this is actually your test stat. And then, of course, once you get here, you see where does it fall? And, of course, it's going to fall somewhere in a non-rejection area. So your conclusion will be do not reject the null. So there's another way to calculate it. If we assume that the population standard deviations are not equal, then basically we don't do the pooled number. We have to go to this equation, and basically this is your test stat number. Just compare it to the one before. So, but once you would get a test stat number, you do the same calculation as before. You compare it to your critical value, but this would be your test stat formula if we assume that it's going to be an unequal population standard deviation. Okay, now and then down here below, notice for degrees of freedom, I don't expect you guys to do this. So if you just take n1 plus n2 minus 2, substitute it for this equation, this is said to be a good approximation of your degrees of freedom. That'll save you some time. It's good enough.